Hey everyone, and welcome. Today, we're going to tackle a real GCSE physics exam question about the refraction of light. And I mean really break it down piece by piece. So yeah, let's just dive right in.
You know the feeling, right? You open the exam paper, see this monster of a question with graphs and diagrams and multiple parts, and your brain just kind of freezes. Well, the secret isn't just knowing the physics. It's about knowing how to attack the question itself.
And this is our challenge for today. This is question 03, straight from an AQA higher tier paper. We're going to walk through every single part from the setup to the final calculation and figure out exactly what those examiners are looking for to get top marks.
All right, first things first. Before we can answer anything, we've got to understand the setup, the context of the whole thing.
So, what we're looking at here is an investigation into light refraction. You know, that's just the bending of light as it moves from one thing, like air, into another, like this glass block right here. And the star of the show? It's the ray box, which gives us that nice, clean beam of light to work with.
Okay, let's get into the first part of the question. This is a pretty quick two-marker, and it's asking why it's better to use a narrow ray of light instead of a wide one. And really, this is all about getting good, reliable results.
And here's the key idea. Think about it. If you have this big, wide, fuzzy beam of light, where do you measure from? The top edge? The bottom? The middle? It's basically a guessing game. But with a nice, sharp, narrow ray, boom, you can pinpoint the exact center, which means your angle measurements are going to be way, way more accurate.
All right, moving on. The question now throws a graph at us, showing the students' results from the experiment. So let's figure out how to read this thing.
Right, so check this out. The question is asking for a value that is literally off the chart. See, the student stopped measuring at a 70-degree angle of incidence, but we need to figure out what would happen at 80 degrees. This means we need a special skill.
And that skill is called extrapolation. I know, it sounds a bit technical, but all it really means is that we're going to extend the pattern we can already see to make a really solid, educated guess about what happens next.
So how do you actually do that? Well, first, you take your pencil and you draw a nice, smooth curve of best fit that goes through as many of the points as possible. Then you just keep drawing. You continue that curve, following the same trend until you're right above the 80-degree mark on the bottom axis. From there, you just read across to the vertical axis and, yep, it looks like we land somewhere around 41 degrees.
And now it's time for the big one. You know what I'm talking about, the dreaded 6-mark question. This is where you really have to prove you get it. Not just what happens, but how and why the whole experiment works.
So what they're really asking is for you to write the instruction manual for this experiment. Think of it this way. If you gave your method to a classmate, could they follow your steps exactly and get the same results? That's the goal. It needs to be a super clear, logical, perfect step-by-step guide.
Okay, so if you want to nail this and get all 6 marks, here's the kind of thing you'd write. First, you'd start by placing a glass block on a piece of paper and just drawing an outline around it. Next, you draw your normal line. That's just a line at a perfect 90-degree angle to the surface of the block. Then, you grab your ray box and shine a beam of light right at the block at a specific angle. You'll want to mark where the ray goes in and where it comes out with a couple of little dots. After that, you can move the block out of the way, connect the dots to draw the path of the refracted ray, and then get your protractor out to measure those angles, the angle of incidence and the angle of refraction. And the crucial last step? You can't just do it once. You have to repeat the whole process for a bunch of different starting angles to get a full set of reliable results.
Okay, awesome. We've got the method sorted. But, what happens when you actually get the data? Especially when you do repeat readings and they're not exactly the same. That's where this idea of uncertainty comes in.
So the question gives us a really specific situation. For a 40-degree angle of incidence, the student didn't get one answer, they got 3 different ones for the angle of refraction. So how on earth do you take those 3 numbers and turn them into one single final answer that includes the uncertainty?
Okay, so here's the data they give us. We've got 28 degrees, 25 degrees, and 22 degrees. Now, they're all in the same ballpark, but they're obviously not identical. So, what's the official procedure here? What does the mark scheme want?
Well, let's look straight at the mark scheme guidance. The first thing it tells us to do is check for any anomalies, any results that look really out of place, and ignore them. In our case, 28, 25, and 22, they're all pretty close. No obvious weird ones in there. So we can move on to the next step, which is to calculate the mean.
All right, let's crunch the numbers. First, the mean. You just add the 3 numbers up, 28 plus 25 plus 22, and divide by 3. That gives us 25 degrees. Now for the uncertainty. To get that, we first need the range. The range is just the biggest value minus the smallest value. So that's 28 minus 22, which is 6 degrees. And here's the rule. The uncertainty is always half of the range. So half of 6 is 3. Our final complete answer is 25 degrees plus or minus 3 degrees.
Okay, we are on the home stretch now. We're almost done with this question. This last part is just a quick check to see if you remember a really fundamental bit of physics.
The final question is multiple choice, and it tests this core idea. When a light wave is refracted, what property of that wave actually changes? Is it the color, the frequency, or the velocity?
And the answer you're looking for here is velocity. It's as simple as this. When light goes from air into something denser, like glass, it slows down. It has to push its way through more stuff, so to speak. And that change in speed is the very reason it bends, or refracts in the first place. But its frequency, that doesn't change. And since frequency determines the color of the light, the color stays exactly the same. That's a super important concept to lock away.
So let's just do a super quick recap of everything we've covered by breaking down just this one question. We've seen that precision is absolutely crucial. That's why we need those narrow rays. We've practiced our graph skills, including extrapolation. We've laid out a full, logical 6-mark experimental method. We've handled data by calculating the mean and uncertainty. And we've reviewed a core physics principle about what changes when a wave refracts. All of that packed into just one question.
And there you have it. We've completely deconstructed that question. But I want you to notice something. This wasn't really just about light, was it? It was about a way of thinking, describing a method, handling data, spotting patterns, thinking logically. That's the language of science. So my final question to you is, what other subjects, in school or out, use these exact same problem-solving skills? It's definitely something to think about. Thanks so much for joining me.